Welcome to Lecture Online, and in this video we're going to show you how to find the moment of inertia of a flat circular disk. Now the disk has a slight amount of thickness, let's call it delta z, and delta z is just a constant. The radius of the disk is r, the mass of the disk is m, and the density is called rho. And we're going to take the disk and rotate it about the y-axis like that. So what is the moment of inertia? The best way to go about it is just take a small little segment like this. Let's say the height of the segment is equal to y, and the distance from the y-axis is equal to x. The thickness would be equal to a dx, and of course the thickness in this direction would be a delta z. So we have a small little segment like that, and we're going to calculate the moment of inertia of that going around the y-axis. And so we can say that the volume of that, let's call it a dv, is equal to the height y, the width dx, and the thickness delta z. So that's the volume. And the density of that would be rho. And of course, remember that the density of the disk is equal to the mass divided by the volume. So in this case, that would be equal to the mass of the disk divided by the volume of the disk, which would be area times the thickness, which would be pi r squared times delta z. So and we'll plug that in to the equation later. Now the mass of that small little segment, let's call it a small little dm, is equal to the density times dv, and that would be equal to the density times y times dx times delta z. So that's the dm. Now we're going to need that because the moment of inertia of this little segment as it goes around the y-axis, by definition, we'll call it a di, and that is equal to the mass, dm, times the distance to the axis of rotation squared, which would be x squared. So that's the moment of inertia of that little piece. Of course, what we're going to do now is integrate it over that quadrant and then multiply it times 4 because we have 4 quadrants like that. So that means that the moment of inertia of the whole disk is equal to 4 times the integral of all the di's. And of course, we're going to integrate that from x equals 0 to x equals r, from x equals 0 to x equals r. And so that becomes equal to 4 times the integral of, now di is dm, and dm is right over here. So that's equal to the density times y times dx times delta z. And then we have to multiply times x squared. And the limits are still from 0 to r, assuming, of course, that that is the x limits. All right. Now next, what we're looking here is, let's move out some constants to make it look a little bit cleaner. So I is equal to 4 times, let's take the density out, and delta z is a constant, delta z, which leaves us with a y, an x squared, and a dx from 0 to r. Okay, now it's a little better to look at. So we have a variable y, we have the variable x, and we have a dx. So we have to kind of come up with a common variable here. But maybe what might be easier is to realize that if we draw a line from there to there, and we realize that this is the radius of the circle, and this here, and if this angle here is theta, then this is the adjacent side x, that's the opposite side y. So we can write that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. All right. If we do that and replace y and x by these two right there, we'll end up with the following. We'll end up with 4 times the density times delta z times the integral of y, and y is going to be r sine theta, times x squared, so that's going to be r squared cosine squared of theta. And now we also have a dx. Well, let's go ahead and take the differential of that. So dx is equal to the derivative of that, which is r times the derivative of cosine is the minus sign. Oop, that's not a very good looking sign here. The minus sine of theta, and that would be then d theta, because the dx d theta moves the d theta over there. Now also notice that this is just a small little width dx, and it doesn't matter if that's positive or negative, even though the differential, the derivative is a minus here. The differential, so simply the difference, we can just take the absolute value of that. We don't need the minus sign. So dx then also can be written as r times the sine of theta d theta. All right, so now notice that in the integral, all we have now is the variable theta, x and y is gone. And of course, the limits from 0 to r now become from 0 to pi over 2 as we go around a quarter of a circle. So now the limits of integration is going to be 0 and pi divided by 2. All right, so let's go ahead and simplify that now. Notice we can pull out an r to the fourth, and this is now going to look like this. The moment of inertia is going to be equal to 4 times the density times delta z times r to the fourth times the integral from 0 to pi over 2 of sine squared of theta times the cosine square of theta d theta. All right, so now we need to integrate this. Now, to help us along, I was of course anticipating that this would happen. I have a few identities drawn on the board here, and notice that what I have over here is this quantity squared. So what I'm going to do is I'm going to take this and write it as the sine square of theta times the cosine square of theta is equal to, bringing the 2 over here, I get 1/2 times the sine of 2 theta, and of course I need to square that as well. All right, so I can replace this by this over here. And of course, 1/2 squared is 1/4. I can take that outside integral sign, so this becomes 4 times the density times delta z times r to the fourth times 1/4 times the integral from 0 to pi over 2 of the sine square of 2 theta, the sine square of 2 theta d theta. There we go. And of course, the 4 will cancel out with the 1/4 right there. Surprise that a little bit. But we're still not quite out of the woods, because how do you integrate sine square of 2 theta? Can't. So I have a second identity right here. And so here I can write that the sine square of 2 theta, if I make this 2 theta, then this will become 4 theta, right? If this is an angle, that's a double angle. So this is 2 theta, that becomes 4 theta. And I need to, well, actually, this will get too confusing unless I put in a few steps. So let me rewrite this. I'm going to bring this over here. So 2 times the sine square of 2 theta, I'm going to make that a double angle, move it over here, is equal to 1 minus the cosine of 4 theta. And then dividing both sides by 2, I get the sine square of 2 theta is equal to 1/2 times 1 minus the cosine of 4 theta. Like that. And so that means I can replace this by that. Again, I have 1/2 in here that I can pull outside the integral sign. And now my integral will look like, so I have to come up here and continue. So I have density times delta z times r to the fourth. I'm going to pull out the 1/2. Now I have the integral from 0 to pi over 2. And notice, instead of having the sine square of 2 theta, I'm going to put this in the integral sign. So I have 1 minus the cosine of 4 theta d theta. All right, so now I'm almost there. I can almost integrate this, because I have to turn this into 2 integrals. This is going to look like density delta z r to the fourth times 1/2 times the integral from 0 to pi over 2 of d theta, because 1 times d theta is d theta, and then minus the integral from 0 to pi over 2. Now notice I have the cosine of 4 theta, which means I need a 4 d theta, which means I need 1/4 the cosine of 4 theta times 4 d theta. Like that. So now we can go ahead and integrate. This is equal to the density times delta z times r to the fourth power times 1/2 times, this is theta, evaluated from 0 to pi over 2, and that's an easy evaluation, minus, okay, so the integral of the cosine is the negative sign. Well, the negative times the negative makes this a positive, so this would be the sine of 4 theta, evaluated from 0 to pi over 2. And close bracket. All right, now notice when I evaluate this integral, the sine of 4 theta evaluated at pi over 2. Well, 4 times pi over 2 is 2 pi, and the sine of 2 pi is 0, and the sine of 0 is 0, so this portion simply cancels out, becomes 0, and this evaluated will be pi over 2. When I plug in a 0, I get 0, so this becomes equal to the density times delta z times r to the fourth power times 1/2 times pi divided by 2. Okay, one more thing left to do, which is going back over here and realizing that the density can be written as m divided by pi r squared delta z. So this cannot be written instead of density. I'm going to write m divided by, in the denominator I get pi r squared times delta z. And then in the numerator I have what's left here. Oh, don't forget the 2 and the 2 here. So that's 2 times 2 is 4 times 4. And in the numerator I get delta z. I get r to the 4th, and I get a pi. Now the fun part starts. I can simplify everything I can here. I have a delta z and a delta z that cancels out. A pi and a pi cancels out. An r squared and r to the 4th becomes r squared. And finally, when I take what's remaining, this is equal to 1/4 mr squared. And that is the moment of inertia of a thin disk rotating about the axis going to the center. So when the whole thing rotates like this, the moment of inertia is 1/4 mr squared. And that's how we do that.